So I will talk to you about searching for gravitational waves from black hole binaries in the data from the Ligo detectors. And I will focus on the challenges that we face when we perform those searches, and also on what we can gain by performing those searches. And I will say that this is work that I've done within the InSpiral working group in the Ligo scientific collaboration. Some of the things I will say, people here will know, but I will mention them anyway for those that don't know them. And if you have any questions, you should feel free to stop me and ask. So here's an outline of what I'm going to talk about. I'm going to talk a little bit about the status of the Ligo interferometers right now. I will mention the target signals of the InSpiral group and how we search for those signals. I will focus on black hole binaries because that's what I've been working on mainly within the InSpiral working group. And as I said previously, I will mention the challenges that we face and how we deal with those challenges. And I will spend a significant amount of time on what can we gain by the black hole binary searches. And I will conclude with future directions that the InSpiral working group has taken. OK, so as all of you probably know, LIGO has 3 interferometers. The LIGO scientific collaboration has 4, including GEO, but GEO is not used in the binary black hole search because of its sensitivity curve. But there's 2 interferometers at Hanford, and I'm basically showing this slide to introduce some abbreviations that I will be using. So LHO is the LIGO Hanford Observatory. The interferometers there are H1 is the 4-kilometer, and H2 is the 2-kilometer. And the LIGO Livingston Observatory is abbreviated as LLO, and the 4-kilometer interferometer there is abbreviated as L1. So the status of the LIGO interferometers is that they've reached design sensitivity. We've completed 4 science runs, which we name S1, S2, S3, and S4. And the 5th science run is in progress. In this plot, you can see the noise curves from S1 through S5. S5 is the purple curve. And the smooth curve is the design goal for initial LIGO. And you can see that in frequencies above 100 hertz, that has been reached. So in this talk, when I show results on the binary black hole search, I will talk about results in the data from the 2nd science run because they have been reviewed and approved for publication. The searches in the S3, S4, and S5 data are currently in progress. So I won't be showing any results, but those are very close to being published as well. OK, so the target signals for the InSpiral group. We're basically looking for coalescences of binaries that consist of neutron stars or black holes. And as you know, those basically have 3 stages: the InSpiral, the merger, and the ring down. And the InSpiral and the ring down have waveforms which can be calculated. We know what those waveforms look like. The merger is a bit more tricky because we don't have waveform templates for that. So to search for the merger, we usually use methods that allow us to search for unmodeled bursts. The duration and frequency content of the signal varies depending on the component masses and also the angular momenta of the 2 components of the binary. But because the InSpiral waveform is pretty well known, what we do in the InSpiral group is we search for these coalescences by searching for the InSpiral phase in the data. And specifically because the duration and frequency depends on the masses, we don't search for all the InSpirals at once, but we sort of break up the search. We break up the mass plane, and we perform the searches individually. So we search individually for primordial black hole binaries with component mass between 0.1 and 1 solar masses, neutron star binaries with component mass between 1 and 3 solar masses, black hole binaries where each component has mass 3 or more solar masses, and neutron star black hole binaries where one component is between 1 and 3, and the second one has mass greater than 3 solar masses. So what I'm going to be focusing on is the black hole binaries. And I'm going to tell you, give you some idea of how we search for those. And so the main ideas on how we search for those are uniform across all the searches. So in all these cases, the signal is really buried in the noise. So in this case, this is a data stream of data from the second science run with a simulated signal injected in it. So you can't distinguish where the signal is. It all looks very uniform. To distinguish the signal, the main thing we do is we calculate the signal-to-noise ratio, which is basically a correlation of the Fourier transform of the data, S of f, with the template, the spiral template waveform, and actually it's the complex conjugate of it. And that correlation is weighted by the noise, and actually the inverse of the noise, so that wherever there's a lot of noise, the contribution to the integral is small. And we integrate over frequencies. And when we calculate this, in this case, we get the spike here, the high SNR, which is clearly distinguishable above the background, and that's where the signal is in this case. Now, this matched filtering algorithm is only the core of our analysis method. There's actually a lot more that we do in one specific search. So the first thing we do once we collect data is we identify the data that is actually appropriate for analysis. So we go through the data, for example, for the second science run, and we identify segments that are long enough for us to estimate the power spectrum, and data that are not too noisy, and we impose a lot of data quality cuts. So we know which data is appropriate for analysis. Then we run the analysis pipeline on the data, and the analysis pipeline consists of these 6 things in principle. The first thing we do is we generate a template bank for the data for each interferometer. And the template bank basically spans the mass space that we're interested in each search. We use those templates to match filter the data from each interferometer, and we threshold on the signal-to-noise ratio. So anything below a certain signal-to-noise ratio is rejected. We record everything that passes the signal-to-noise ratio threshold as triggers. And by that, we mean that we record the template parameters, the times, and other information for the times when the SNR threshold is passed or is exceeded. So after we do this for each interferometer, we impose coincidence in time and in the waveform parameters between interferometers. And that actually is a stage where our triggers are reduced very, very much. After we do that, we apply signal-based vetoes, which they are waveform consistency tests. So basically what we do is we check that actually what caused the high signal-to-noise ratio looks like an in-spiral, as opposed to it being a loud noise event, which caused a high signal-to-noise ratio. So that also rejects a large amount of events. And at the very end, we apply instrumental vetoes. And instrumental vetoes are based on tests that we perform that find correlations between the gravitational wave channel and other channels in the interferometer that tell us that something is going wrong in the instrument at the time of the high signal-to-noise ratio. So that also reduces the number of candidates. Of course, even at the end of this method, we can get accidental coincidences. And we have to have a sense of what the rate of accidental coincidences is. So we do what we call time shifts on the data. So we shift the data between the interferometers by amounts of time that allow us to be certain that if there were a gravitational wave in the data, we wouldn't see correlations in the time-shifted data. So all the coincidences at this stage are completely accidental, and we can estimate the background like that. Another very important part of the analysis method is running the pipeline on data where simulated signals have been injected. And that allows us to tune the pipeline parameters, for example, the coincidence windows, so that we don't miss signals that we know we should be seeing. And also, we can get an estimate of how sensitive our searches are. So those main ideas are applicable for all the different searches I talked about before. Now, focusing on black hole binaries, we have special challenges that we have to deal with. And I think the best way to give you an idea of what those challenges are is by this plot here. The two blue curves are the initial LIGO and advanced LIGO noise curves. And the two arrows show how the signal sweeps across the frequency band for two different binaries. So the lower arrow is for a 1.4 solar mass binary at 20 megaparsecs. And you can see that it basically it's above the noise floor. And it basically sweeps across the frequency sensitivity band of initial LIGO. And so the in-spiral ends somewhere at 1400 hertz. The upper arrow is for a 1010 solar mass binary, again at 20 megaparsecs. And you can see that the signal is a bit louder, but it ends at about 200, a bit above 200 hertz. So it ends halfway through the frequency band of LIGO. So to put all this in words, the ground-based interferometers are sensitive to signals above 30 or 40 hertz. The innermost stable circular orbit frequency for many of the binaries that we're looking for in the black hole search is only marginally above that. So for many of the signals we're looking for, we have just a few cycles in band. And that's what we're looking for. And as if this were not enough, the in-spiral waveforms are not known with precision for those last few cycles because different approximation schemes give different predictions for the last few cycles of the black hole in-spiral waveforms. So one question that arises is which one of those waveforms do we use when we match filter the data and look for those in-spirals? Additionally, the waveform consistency test that I talked about and which we use very successfully for neutron star searches and primordial black hole searches is not applicable for the higher mass black hole binaries because there are very few cycles in band, and it will take a lot of time to explain, but you need quite a few cycles in band to apply that test. I can talk about that later if people have questions, but there are too few cycles for that to be applied. The last point is that there is a large part of the energy that is released during the merger phase for black hole binaries. And the frequency is usually at the sweet spot of the ground-based interferometers. And so somehow we have to include the merger in those searches in order to increase our sensitivity. So those are the challenges. How do we deal with those challenges? One way we deal with those challenges is instead of using model-based waveforms, we can use the BCV waveforms, which are phenomenological templates. So the BCV templates were proposed by Bonanno, Chen, and Valisneri in 2003, and you can see the frequency domain waveform, the expression for those. And you will recognize some factors. So f to the minus 7 over 6 is the standard Newtonian amplitude of the post-Newtonian templates. There is another factor, which is 1 minus alpha times f to the 2/3, and that factor is inserted there for two reasons. First, it can give high matches with model-based waveforms that extend beyond the ISCO frequency and into the Planck phase, and it also captures post-Newtonian amplitude corrections. There's also a cutoff frequency. Phi 0 and T0 are related to the phase and the time of arrival of the wave, and psi 0 and psi 3 are sort of related to the masses. There is a loose relationship between psi 0 and psi 3 and the masses of the in-spiral, but the actual masses don't show up in this equation. So the benefits of using those waveforms is that they've been proven to have very high match, 95 to 99% with model-based waveform, with all model-based waveforms that have been proposed in the literature. Additionally, they can pick up signals that don't match one of those waveforms, but are actually in between those waveforms, which is good because if the actual signal is none of those that we think, but in between those, we can still pick it up with those templates. The other benefit is that they can extend a little bit into the merger phase, into the plunge phase. So that gives us higher sensitivity because we can catch a greater amount of energy than we would with just the in-spiral. So they're very good for identifying black hole binary in-spiral waveforms in the data. Some of the disadvantages of using those templates is that they also give high signal-to-noise ratios for instrumental and environmental noise events. Many of them are very short in time, so they catch many of the short noise events that show up in the data, which wouldn't be picked up by the post-Newtonian templates necessarily, so we get a lot of false alarms. And the last point, which is not all that significant, I mean, it's significant, but it's not a deal breaker. They're not appropriate for parameter estimation because the masses don't show up, and these templates are not normalized to some distance. So we can get the parameters of the signal. So just to give you an idea of results that we get by running the BCV templates on the S2 data specifically. So this is a plot of the Hanford versus Livingston signal-to-noise ratio. And these are accidental coincidences in the data from the second science run. This is based on 80 time shifts, and we observed about 25 to 30 accidental coincidences per S2. So your eyes should be drawn here to two different regions. The first one is this region here, where we have triggers which have relatively small signal-to-noise ratio in each interferometer. So signal-to-noise ratio below 12 at Livingston and at Hanford. There's also those tails of triggers which have small signal-to-noise ratio in one of the sites and large in the other one. So if the data were completely Gaussian, those tails wouldn't exist. This distribution of events is consistent with Gaussian noise with noise bursts. In the binary neutron star search that we did with post-Newtonian templates, these tails didn't exist, and we just had the Gaussian part. And the reason why they do exist here is because we don't apply the waveform consistency test that we applied in the binary neutron star search. So these are the accidental coincidences. The question, of course, is what does a real signal look like in this graph, and would we be able to distinguish it from an accidental coincidence? And so if I add the triggers for some simulated signals, that's what the distribution looks like. And so just to give you an idea of the reach in the S2 search, an event with signal-to-noise ratio around 10 or around 1010 would come from the Andromeda galaxy. And the ones with higher SNR are closer than that. So you can see that there's no clear distinction between the accidental coincidences and the actual signals in this case. There's a region here where you can see either one. So the question is, how can we make this search better? How can we have sort of a more clear cut between the two?
Can you explain to me why you're getting much larger signals at Livingston than at Hanford?
So at the second science run, Livingston was about twice as sensitive as Hanford. You will see some events here that are actually from injections and have much higher Hanford signal-to-noise ratio than Livingston, and that's because that specific injection was optimally oriented for Hanford, but not for Livingston.
Standard 40-40?
These range from 3 to 20 solar masses, component mass. Okay, so how can we make the search better? That's what we're working towards. So things that we already do that reduce the false alarms are these three. Coincidence reduces our triggers by a very large amount. We also do an H1, H2 amplitude consistency test for triggers that come out of our pipeline. And So basically because H1 and H2 are co-located and co-aligned, if we see a signal, an actual gravitational wave signal in H1, we know what amplitude it should be observed with in H2. So if that's not the case, if we don't see that amplitude consistency, we can reject those triggers. Unfortunately, we cannot do the same thing between Hanford and Livingston because they're almost perfectly aligned, but not exactly. And that small difference, if we have a signal that's optimally oriented for one of the sides, but not for the other, that can cause large variations in the amplitude. So we don't trust that test between sides, but we do trust it for H1, H2. And also the instrumental vetoes that I talked about previously. Things we do plan to incorporate in the search to make it better and make a more distinct distribution of accidental coincidences and injections. The waveform consistency test that I mentioned, we can now do for the longer black hole binary signals because the frequency above which we search has been reduced from 100 Hertz in S2 to 40 Hertz in S4 and S5. So we have longer signals and we can do this test for the longer signals. We're also looking at other signal-based vetoes that we can apply and again reduce our false alarms. So that's the direction that we're headed. Okay, so what can you expect from the black hole searches in the future? And there's two cases, of course. There is the case in which we do see something and the case in which we don't see anything. So if we don't see anything, what information can we get? What astrophysics can we do? We can calculate a rate upper limit for black hole binaries in the universe. So if we do a frequentist rate upper limit at 90% confidence, that tells us that the rate is less than 2.303 divided by the observation time and the number of Milky Way equivalent galaxies that our search is sensitive to. So the observation time is given for each run, and it was 0.04 years for S2. And the question is, how do we calculate the number of Milky Way equivalent galaxies? And we do that by doing injections, as I mentioned previously. So by doing injections, we can calculate the efficiency of our search for each given distance. So that's what's shown in the red curve in this plot. The horizontal axis has the Hanford effective distance. The vertical axis is actually overloaded. I just like to plot all these three things on one plot. I will talk about all of them, but for now, the red curve, as I mentioned, is the efficiency, and it's basically the number of found simulated signals over the number of injected simulated signals for each distance bin. And again, this is for the second science run. You can see that it's almost 1 all the way up to 1 megaparsec, and then it drops almost completely to 0 at 2 or 3 megaparsecs. So this is the efficiency versus distance. I should mention that the injections that we did in the second science run were injections of binary inspirals with component masses between 3 and 20 solar masses. The distances were between 10 kiloparsecs and 10 megaparsecs. And because we have different waveforms in the literature, we did injections with 3 different waveforms. We used effective one body, Padet T1, and Taylor T3, and they were all of second post-Newtonian order. So once we get the efficiency, we have to estimate how many Milky Way equivalent galaxies that corresponds to, because upper limits are quoted in per Milky Way equivalent galaxy. So to do that, we have to make some assumptions about the black hole population. And the assumptions we make are, for the most part, reasonable. So we assume that black holes come from the evolution of stars, and so they are present in galaxies, and they're present, so they're They're distributed in galaxies according to the galaxy's blue light. That's a reasonable assumption. And by that we get the number of Milky Way equivalent galaxies per distance, which is the black curve in this plot. So you can see one peak here. So this region here is the Milky Way. And you can see going up again at about 800 kiloparsecs. And that's the Andromeda galaxy. So we also assume that the component mass distribution is uniform and ranges from 3 to 20 solar masses. Again, some populations proposed in the literature give that distribution. We assume that the component spins are negligible. That's not a very good assumption because we know that things have spin. And the one that I hate is this last one, that the waveforms are a mixture of effective one-body, Padetti 1, and Taylor T3. And we made this assumption in S2 because those were the injections that we did. But the universe gives one form of waveforms, clearly.
It's one part of each?
Yeah. Yeah.
Part,
Yes, they are. They are. So that was just for the sake of doing our calculation. So by making these assumptions, as I said previously, we get the number of Milky Way equivalent galaxies per distance bin. So if we multiply that with our efficiency per distance bin, we can get the number of Milky Way equivalent, and integrate that over distance, we get the number of Milky Way equivalent galaxies that we're sensitive to, and that's the blue curve here. So this is a cumulative number of Milky Way equivalent galaxies per distance. And what we got for S2 is 1.66. And by plugging everything into the equation, we get 38 per year per Milky Way equivalent galaxy. So this is not an astrophysically interesting upper limit, but it is an upper limit. And it gives us an idea of how we can do calculations like that. So that was for the second science run. The question is, what can we do from now on? So I will tell you in a minute what we can do from now on. But to tell you that, I need to show you how the reach of the black hole binary search has improved in the different science runs. So in S2, the reach, so in the second science run, a 5-5 solar mass binary that's optimally oriented would give a signal-to-noise ratio of 8 in the data at 7, if it were at 7 megaparsecs for Livingston and 3 megaparsecs for H1 at Hanford. You can see that this has improved very much, and for the first 2 months of S5, which was, so those months were from November 14th to January 15th, the same numbers are 55 megaparsecs for Livingston and 70 for H1. And I'm making a note that this is preliminary because the data has improved since then. So this actually may be a bit better for S5.
So, Eirini, the efficiency you showed us before, was that also for SNR of 8 in both?
No, the efficiency was the efficiency at our loudest event, which for S2 had signal-to-noise ratio 9 at Hanford and 13 at Livingston. So these are the current estimates, and as I said, they're preliminary. So if we impose coincidence, we can assume that we can see a 5-5 solar mass binary at 55 megaparsecs.
What's the tolerance for optimally oriented? Like how many degrees would it have to be?
Oh, this is optimally oriented.
Yeah,
This is
like what percent of mergers could be, okay, like if you just threw them randomly in the sky, what percent?
Oh, so if we did an average over orientations, that would be reduced by a factor of 2, approximately. Okay, so the question is, how many Milky Way equivalent galaxies does that correspond to? And we don't know the galaxy distribution out to those distances, but we've constructed galaxy catalogs in the inspiral group, many different, well, a few different ones, that allow us to estimate the number of Milky Way equivalent galaxies per effective distance for each instrument. And this is actually for Hanford Livingston, the Geo detector, the Tama detector in Japan, and Virgo as well. So you can see that between 20 and 25 megaparsecs, it starts to become about a straight line. And I wanted a quick estimate on how many Milky Way equivalent galaxies the 55 megaparsecs correspond to. And I got about 1,200.
Wasn't that was effective distance on it?
Yeah, yeah.
But the distances that you gave us earlier were optimally oriented distance. So, I mean, so you wouldn't just extrapolate this to 55 megaparsecs?
No, because...
Effective is optimal.
Yeah.
So, yeah.
Oh, sorry. Effective.
Yeah.
That is effective distance.
Yes.
Of course, it will be.
Yeah.
Yeah, thank you. So the slope of that line, right?
No, not distances. So again, I wanted to get an estimate of what sort of upper limit we can expect from S5. So if we assume 1 year of data, and we focus on binaries of component mass between 3 and 20 solar masses, so that the estimate I have for a 5.5 is not completely unreasonable, we get that the rate at 90% confidence would be less than 2 times 10 to the minus 3 per year per Milky Way equivalent galaxy. I'm actually optimistic that we can do a bit better than that, because for binaries of a bit higher mass, we can actually see further. And the distance versus mass distribution peaks at around 1313 solar mass binaries. So, but this is a rough estimate of what can be expected. Now, what happens if we do have a detection? What do we want to do with that? We want to calculate the physical parameters of the signal. And the main things that we want to calculate are the masses, the time of arrival, and the source location. I mentioned previously that the BCV templates are not appropriate for parameter estimation. They were not constructed with that in mind. So the masses don't show up in the templates. But some parameters may still be estimated with the BCV templates with some accuracy. So I'm going to show you what accuracy we had in the second science run when we estimated parameters with the BCV templates. So for example, the chirp mass, which I think most people know it, but it's the combination, it's this combination of the two masses of the binary. So using the BCV templates, there's a relationship between the chirp mass and the parameter size 0. So that's what we use here to estimate the chirp mass. And so on the upper graph, you can see the injected chirp mass and the recovered chirp mass in solar masses. And you can see that, so the black line is the equal mass diagonal. You can see that for many of the signals, we can get a reasonable estimate of the chirp mass, but many of those are completely off as well. You will also observe that the low chirp mass signals we can do better for. And that's because those signals have longer duration. They have more cycles in band, so we have more information to extract the chirp mass.
Can it be template spacing too? Or
I doubt it.
templates are closer together at low masses?
Yeah. Yeah, could be.
Or maybe
Yeah.
longer.
Saying that the discreteness of the template bank in terms of the M chirp of the templates is it's finer at low masses than high masses.
I think that's true, isn't it?
Well, okay, so because I thought what you meant was that because we have fewer templates that catch the lower mass signals, there's fewer choices
Yeah, so
for
you
size 0.
default to
Yes,
one that is
yes,
farther
yeah,
parameter.
exactly, yeah, yeah,
This is your equal mix of the 3 different waveform types.
yes, yes. Actually, no, actually this is effective one body, which where BCV,
On the BCV.
Yes, it's effective. So injected effective one body recovered by BCV. Yeah. So the accuracy by which we could recover the chirp mass here is a few solar masses. And just to give you an estimate, in the S2 neutron star binary search, the chirp mass accuracy was 2 × 10⁻³ solar masses, so 3 orders of magnitude better. Now, regarding the time of arrival estimation, the x-axis here has just the injected end time in hours since the start of S2. The vertical axis has the injected minus the recover end time in milliseconds, and the 0 is over here. And you can see that most signals are recovered within 15 milliseconds, but some go up to 25 milliseconds. So again, just to give you a measure of comparison, the accuracy for the neutron star binary search was 1 millisecond. So the binary neutron star search did better. Now, I have to mention that when we try to find the sky position, we actually don't exactly care about the time of arrival at one side, but we care about the end time, the time of arrival difference between Hanford and Livingston. And the bias was the same in Hanford and Livingston. So actually, the accuracy of recovering the time difference was not 25 milliseconds. It was 10 milliseconds. So it's a bit better than that, but still pretty far from the 1 millisecond that we got in the binary neutron star search.
This number is consistent with the formula that relates the signal to noise ratio and the frequency component of what you would expect as
Which number?
the arrival time that you find is consistent with the frequency component of the signal, yes and no.
I'm not
What
sure.
you would expect.
Like delta T, delta F is around 1 kind of a thing.
Something like that.
I'm not sure.
Anyway,
I'll look at that.
Has this been done for BCV inductions into
But there's a more
BCV test? Because then you might get a more accurate, there's a different definition of end time essentially.
So it has been done. I just don't remember what the accuracy was. Presumably it was a bit better, but I don't remember exactly how much.
But there's a more dramatic effect. This is the EOB waveform, right?
Yes.
And they're all some number of milliseconds beyond ISCO.
Yes,
EOB.
yes, yes.
So this bias is dramatic for EOB, but it's not there, I presume, for the others.
It is.
There for the others?
Mm-hmm.
So EOB is always a good cycle or more longer than the others.
Yeah. So I think this time this time accuracy is more due to the frequency binning of the BCV templates. The frequency binning is not it's not very fine. But anyway. Okay.
There's your delta T, delta
Higher
T.
frequencies, so
Right.
I think you can resolve time better.
That's what Massimo was saying.
Yeah.
Okay, so how can we do better than this? What we plan to do, and it's actually work in progress, is if we do have a candidate, to follow up with model-based waveforms which contain the mass information and the distance information. So we expect that from those we would get an accurate estimate of the masses, an accurate estimate of the difference of the time of arrivals at each site, and then the time difference will give us an annulus on the sky of where the signal could be located. And the more accurately we know that time difference, the smaller that annulus on the sky would be. And also, we expect to get an accurate estimate of the effective distance of the source. As I mentioned, this is work in progress, and the group at Cardiff has started working on this. Some issues that we're trying to address is what accuracy can we get by that method, and also what's the performance across the different families of waveforms. For example, if we inject effective one-body waveforms and we try to recover the parameters with Padetti-1 waveforms, what's the accuracy? How well can we do? And all different combinations of different families of waveforms. Okay, so future directions of the INSPIRAL working group. one issue that remains is to include the spin of the black holes in this search. And there are the BCV2 templates, and the first search with those templates is done on the S3 data and is almost complete, so working on that, and it will be available very soon. I mentioned the model-based waveform follow-up of signals, and I said that's work in progress. Another direction is to do an in-spiral burst coincidence. I mentioned that the merger is an important part of those waveforms, and if we include it in the search, it will give us a very, very high, it will increase our sensitivity. So the question is, how do we take that into account, and what can we do with it? Another thing is that we would like to include the Virgo detector in our searches once data from Virgo becomes available. Our pipeline, our analysis pipeline is ready, and Virgo can be slotted in as another interferometer. So doing that is very easy, and it will actually result in way fewer false alarms for the same detection probability. And it will help us to locate the position in the sky, because it's one extra site that we have information for. Another idea that we're trying to pursue is, so we do want to do the waveform consistency test for the longer black hole binary signals. And one idea is to break up the mass space differently than we do so far, so that we can treat the smaller black hole binaries differently than the higher mass ones. So those are the directions that we're moving towards.
By waveform consistency test here, you mean like a chi-square?
The chi-square test, yes.
Have you thought about doing a consistency test? You said H1, H2 amplitude consistency before. It seems like you might benefit from doing a waveform consistency between the two detectors. That also naturally extends into a merger, a ring-down phase, beyond just the inspiral consistency test. It's a coherent search of H1 and H2.
So that's in progress for the binary neutron star search. We haven't done anything in that direction yet for the black hole search, but we will. So that's all I have.